Today we are discussing about the wave equations. We're discussing about the wave equations. Okay, it's a very, very important concept. It's there in the model question paper also, the derivation of one-dimensional wave equation. The two questions that they frequently ask is, one is one-dimensional wave equation, another is one-dimensional heat equation. Among the two, one is sure to come. That is 6 or 8 marks, 7 or 8 marks. One question is sure. So today I will do it slowly. Actually, there are two parts in this. It's called application of partial differential equation, the derivation of one-dimensional wave equation, and the solution of wave equation. The derivation of one-dimensional wave equation and the solution of wave equation. Okay. Similarly, the derivation of one-dimensional heat equation and the solution of heat equation. So in class today, we will discuss. I am waiting for some students still in the process to come. Okay, I cannot join anyone. All of them should add yourself. You know that. Okay. Now, so one-dimensional wave equation. You can see the diagram here. Some students are simply messaging here. Okay, now here see one-dimensional wave equation. You can see there. So application of partial differential equations. First you can see the diagram here. It's a wave equation. See the wave. You know, wave means it is a periodic. It's in the form periodic, and then a tangent is drawn. It's a rough diagram. Rough diagram. You can know that a tangent is drawn at the points A and B. A is little bit down, B is little upper. So difference is might be small amount that is taken as delta x. Okay, here upper part, the tensions, that is taken as T2, lower part tension as T1. Here the perpendicular is drawn. Here also the perpendicular is drawn. So once again, this is VI means very important question. Okay, very important question. It's a model question paper problem. Derivation, it's a derivation. So let us consider a flexible string. First, let us consider a flexible string tightly stretched between two fixed points. So let us consider a flexible string. Flexible means you can think of a rubber band. A rubber band, it is flexible. Let us consider a flexible string tightly stretched between two fixed points. If you fix two fixed points, in between you stretch the rubber band. So that condition you have to think of. Let us consider a flexible string tightly stretched between two fixed points. In between the distance is taken as L. Between the distance is taken as L. Let rho be the density. Density means mass per unit length of the string. Let rho be the density or mass per unit length of the string. Let rho be the density, that is called, or mass per unit length of the string. Here, mass per unit length of the string. Now we shall assume the following. This all comes from your physical part. One is the tension T of the string is small throughout. Some assumptions are made in these derivations. All this you have to write in the exam. The tension T of the string is very, very negligible, is small throughout. The tension T of the string is considered to be negligible, very, very small. That is considered to be very small throughout. Okay. Then second point is the effect of gravity can be ignored. The effect of gravity can be ignored due to large tension T. The effect of gravity can be ignored due to large tension T. The effect of gravity can be ignored due to large tension T. So gravity is ignored here because we take the tension as very, very large. Third assumption is the motion of the string is in small transverse vibrations. We consider the motion of the string in small transverse vibrations, just like waveform, wavelets. Small transverse vibration. The motion of the string is in small transverse vibration. So let us consider the forces acting on a small element AB of length delta x. I told you the small length AB infinitesimal small length AB, that AB is delta x. So let us consider the forces acting on a small length AB of length delta x. Let us consider the forces acting on a small length AB of length delta x. Okay, you tried all this, you cannot miss any statement here. The forces are acting on a very small length AB of length delta x. Let T1 and T2 be the tensions at the points A and B respectively. Let T1 and T2 be the tensions at the points A and B. T1 and T2 be the two tensions at the points A and B. T1 and T2 be the tensions at the points A and B. Okay. So these are the explanations. Since there is no motion in the horizontal direction, so there is no motion in the horizontal direction. It goes upwards, the wave goes upwards. Since there is no motion in the horizontal direction, the horizontal components T1 and T2 must cancel each other. So the wavelet, it is going up. Since there is no motion in the horizontal direction, the horizontal components T1 and T2 must cancel each other. Horizontal components T1 and T2 must cancel each other. So T1 cos alpha equals T2 cos beta equals T. Again I repeat,
It is not clear.
the wavelength is going upwards. It is in the, there is no movement of the wave in the horizontal direction. It is moving upwards. The horizontal components cancel each other. The horizontal components T1 and T2 cancel each other. So we take it as T1, horizontal component is always cos, and then vertical component is sine. So we take T1 cos alpha equals T2 cos beta equals T. The horizontal components cancel each other, so we take them as T. T1 cos alpha and T2 cos beta, the horizontal components, we take them as T. Give it as equation 1. Name it as equation 1. Where alpha, what is this alpha and beta? Where alpha and beta are the angles made by T1 and T2. Where alpha and beta are the angles made by T1 and T2. If you go back to the figure here, alpha and beta here, you can think the angles made by T1 and T2. Okay. Where alpha and beta are the angles made by T1 and T2 with the horizontal. So T1 is, suppose T1 is down with the horizontal, what angle it makes, that is alpha. And T2, what angle it makes with the horizontal, that is taken as beta. So alpha and beta are the angles made by T1 and T2 with the horizontal. Vertical components of tension. Now we go to the vertical component. Horizontal component is cos, vertical component is sine. So vertical components of tension are minus T1 sin alpha and T2 sin beta. Now why minus comes, I'll explain. So vertical components of tension are minus T1 sin alpha and T2 sin beta. Okay, minus T1, so vertical components are taken as minus T1 sin alpha and T2 sin beta. Why negative sign? Negative sign because T1 is directed downwards. Because T1 is directed downwards, we take negative sign. Because T1 is directed downwards, we take the negative sign, where negative sign indicates that T1 is directed downwards. So we take minus T1 sin alpha, because it's a vertical component, sin comes into the picture, and alpha because T1 makes an angle alpha with the horizontal. So why minus sign? Because T1 is directed downwards. So minus T1 sin alpha, and another for T2 it is T2 sin beta. Hence the resultant force acting vertically upwards will be, so the resultant forces acting vertically upwards will be the sum of the two. Resultant forces acting vertically upwards will be the sum of the two, that is T2 sin beta minus T1 sin alpha. T2 sin beta minus T1 sin alpha. The resultant force acting vertically upwards will be T2 sin beta minus T1 sin alpha. Okay. Now we apply. So the resultant force will be T2 sin beta minus T1 sin alpha, the sum of the two forces. Y1 is negative because T1 is directed downwards. Okay. Now applying Newton's second law of motion. So applying Newton's second law of motion. And Newton's second law of motion is force is equal to mass into acceleration. Newton's second law of motion, applying Newton's second law of motion, that is force is equal to mass into acceleration. So force means the total tension. Force means the total tension. So total tension will be T2 sin beta minus T1 sin alpha. T2 sin beta minus T1 sin alpha. And mass, you know, the density is rho. I taken the beginning here. Here, the density is rho. Written here, mass per unit length. Let rho be the mass per unit length. So density is rho, and the length is delta x. So mass will be equal to length into density, that is rho into dx, into acceleration. Acceleration, you know, by differentiation, dou u by dou t is velocity, and if you differentiate 2 times, you will get acceleration. Dou u by dou t is velocity, and if you differentiate 2 times, you will get acceleration. So mass into acceleration. This is nothing but dou squared u by dou t squared. This is nothing but dou squared u by dou t squared. You know, if you differentiate velocity, velocity means differentiating with respect to t, du by dt, and acceleration is equal to d squared u by dt squared. So the force, the mass into acceleration, mass is rho into delta x into dou squared u by dou t squared. So it is mass is rho into delta x, and acceleration is dou squared u by dou t squared. Okay. Now here, okay, now this is the important point. There is marks here. First, there is marks here for writing the total force acting vertical upward. That is T2 sin beta minus T1 sin alpha. So now applying Newton's second law of motion, force is equal to mass into acceleration. So T2 sin beta, force is given a T2 sin beta minus T1 sin alpha. Then this is mass into acceleration. So mass, rho into delta x into dou squared u by, acceleration is dou squared u by dou t squared. Velocity is dou u by dou t. So some students, they're coming late. So now here you can see rho delta x is the mass of the element portion AB. I'm explaining here, rho delta x is the mass of the element portion AB, and dou squared u by dou t squared represents the acceleration. Rho delta x is the mass of the element portion AB. Rho delta x is the mass of the element portion AB, and dou squared u by dou t squared represents the acceleration. Dou squared u by dou t squared represents the acceleration. Rho delta x is the mass of the element portion AB, and dou squared u by dou t squared represents the acceleration. That I have given just the explanation here, that's all. Now here, how to proceed now next? We divide throughout by t. We divide throughout by t, okay? We divide throughout by t. So when you divide throughout by t, what happens? Divide throughout this by t. So T2 by T sin beta minus T1 by T sin alpha equals, here also I divided by T, rho by T delta x into dou squared u by dou t squared. This is partial differentiation with respect to T 2 times, which is nothing but acceleration. So rho by T delta x into dou squared u by dou t squared. Now from 1, you go back to 1, here from 1, what we can write? Cos alpha is equal to T1 by T, cos beta is equal to, cos alpha is T by T1, and cos beta is equal to T by T2, like that. We can use this equation as you want. So from 1, what we get? T1 by T equals 1 by cos alpha. Can I say T1 by T, because T1 cos alpha equals T, T1 by T equals 1 by cos alpha, T2 by T equals 1 by cos beta. So T1 by T from 1, you see properly equation 1, you can make out, it is self-explainable. Notes I have explained everything. From 1, T1 by T equals 1 by cos alpha, and T2 by T equals 1 by cos beta. T1 by T equals 1 by cos alpha, T2 by T is 1 by cos beta from 1. Now I substitute here. So what will be T2 by T? T2 by T will be, T2 by T will be 1 by cos beta. So here I wrote sin beta by cos beta. So here I wrote sin beta by cos beta. T1 by T. T1 by T will be 1 by cos alpha. So here I wrote 1 by cos alpha. So total it will be sin beta by cos beta minus sin alpha by cos alpha. Then rho by T, delta x here. This equation, see here. T1 by T is 1 by cos alpha. T2 by T is 1 by cos beta. Now I substitute here. T2 by T is 1 by cos beta, so sin beta by cos beta minus T1 by T is 1 by cos alpha. So sin alpha by cos alpha equals rho by t into delta x dou squared u by dou t squared, or dou squared u by dou t squared. Okay, it will be dou squared u by dou t squared. Now what happens? This is tan beta and this is tan alpha. This is tan beta and this is tan alpha. So tan beta minus tan alpha. Tan beta minus tan alpha equals rho by t delta x dou squared u by dou t squared. So tan beta minus tan alpha equals rho by t delta x dou squared u by dou t squared. Okay, dou squared u by dou t squared. This you know. So now this equation can be converted to, but tan beta and tan alpha, what are these? What is this? Tan beta and tan alpha, according to our explanation from trigonometry and coordinate geometry, tan alpha is the slope, tan theta is the slope of any line. So here also, tan beta and tan alpha, alpha is at the point A, beta is the angle made, alpha is the angle made by you can see the tensions at the point A with the x-axis, or with the horizontal, there. And then beta is the angle made by the another tension at the point B with the horizontal. So tan beta and tan alpha represents the slope at B of x plus delta x. B is little above A, so the difference between them is delta x. So tan beta and tan alpha represents the slope at B of x plus delta x and A of x respectively. Tan beta and tan alpha represents the slope at B of x plus delta x and A of x respectively. Okay, now tan beta will be, since it is the slope, tan beta and tan alpha is the slope. So tan beta is written as, since it is the slope, it is written as dou u by dou x. Slope means you know dy by dx, but in partial derivative it is dy by dx at the point x1, y1. Here tan beta is the slope at the point b of x plus delta x. So tan beta equals dou u by dou x at the point x plus delta x. Tan alpha equals dou u by dou x at the point x, because both with the horizontal. So again I repeat, tan beta is the slope at the point B, that is at x plus delta x. So tan beta equals dou u by dou x, x plus delta x. Dou u by dou x, x plus delta x. And tan alpha is the slope at the point A. So at the point that is taken as x. So tan alpha equals dou u by dou x at x. So these two things we are writing here now. So we write, in place of tan beta, I am writing dou u by dou x at the point x plus delta x minus tan alpha, that is dou u by dou x at the point x, which is equal to what? Rho by t delta x, which is equal to rho by t delta x, rho by t into delta x, dou squared u by dou t squared, which is equal to rho by t delta x into dou squared u by dou t squared. Rho by t delta x dou squared u by dou t squared. Now divide by delta x, and apply limit delta x tend to 0. So both sides I divide by delta x and apply limit delta x tend to 0. So dividing by delta x both sides, what we get? Dou u by dou x, x plus delta x, minus dou u by dou x at the point x divided by delta x, limit delta x tend to 0, equals delta x cancels here, dou squared u by dou t squared. So here I divide by delta x both sides. So I get limit delta x tend to 0, dou u by dou x, x plus delta x, minus dou u by dou x at the point x. This is tan alpha, tan beta, and this is tan alpha substituted here, you know that. And then I divide by delta x both sides and apply limit delta x tend to 0. So limit delta x tend to 0, dividing by delta x, here delta x get cancelled. This is nothing but, see the most important point here, this is nothing but first derivative is already there, and the rate of change of the first derivative, delta x, that is nothing but dose by the definition. You might know the definition in your PUC, the definition of differentiability. Limit delta x tend to 0, f of x plus delta x minus f of x divided by delta x, that is equal to f dash of x. Again I repeat, the differentiability definition from your PU level, I think second PUC, limit delta x tend to 0, f of x plus delta x minus f of x divided by delta x is equal to f dash of x. Using that concept, dou u by dou x, x plus delta x, minus dou u by dou x at the point x divided by delta x will be the next derivative, that is dou squared. This is all partial derivative. Dou squared u by dou x squared. This will be rho by t, dou squared u by dou t squared as it is. Now we take here t by rho as c squared. We take here t by rho as c squared. We take here t by rho as c squared. We take here t by rho as c squared. So rho by t is, so what we write here, dou squared u by dou t squared equals, this is cross multiplied, t by rho into dou squared u by dou x squared. From here, I keep only dou squared u by dou t squared one side. Take this to the other side. So it will be t by rho dou squared u by dou x squared. So this is utt. You know the short form of partial derivative utt. This is equal to c squared uxx. C squared uxx. So this is the required, we say the required wave equation in one dimension. Now we have to study the various possible solution of one-dimensional wave equation, because for you in the first class it might be difficult. I wanted to go slowly, so I didn't write this. I will do it in the next class tomorrow at 11 a.m. The various possible solutions of one-dimensional wave equation. So again in your syllabus there is the derivation of one-dimensional wave equation. It's all possible solution. Derivation of one-dimensional heat equation. It's all possible solution. So once again, I will just revise this. Okay, some students are waiting here. Okay, once again, I'll revise this fast. So one-dimensional wave equation. So application, this comes under the last part of third module, application of partial differential equation, that is one-dimensional wave equation. Now here, you can see here the diagram which you have to do. Model question paper problem it is. Very, very important. VI means very important. Okay. Now here you can see this is the wavelet form, and a tension, the tensions that is drawn in the form of a tangent at the point A, that is at the point X, and B is little above A. B is little above A, that is X plus delta X. Okay. And then we draw horizontals and vertical lines here. The tension that is upwards is taken as T2, and the tension that is downwards is taken as T1. So we consider a flexible string tightly stretched between two fixed points at a distance L. We consider a flexible string tightly stretched between two fixed points at a distance L. And we take rho as the density, that is mass per unit length of the string. We assume the following conditions here. The following conditions are assumed in the derivations. The tension T of the string is taken to be very small. The tension T of the string is taken to be very, very small. Then the effect of gravity can be ignored due to large tension. The effect of gravity can be ignored due to large tension. The effect of gravity is ignored here. Then third assumption is the motion of the string is in small transverse vibration. The motion of the string is in small transverse vibration. So now we are explaining the diagram. Let us consider the forces acting on a small elemental length, small length AB. The length is taken as delta X. Let T1 and T2 be the tensions at the points A and B. Let T1 and T2 be the tensions at the points A and B. Okay. Let T1 and T2 be the tensions at the points A and B. Okay. Since there is no, here the motion is going upwards, so vertical. Since there is no motion in the horizontal, there is no motion in the horizontal, only vertical. Since there is no motion in the horizontal components T1 and T2 must cancel each other. Since there is no motion in the horizontal direction, the horizontal component T1 and T2 must cancel each other. So the horizontal components are T1 cos alpha. Always the horizontal component is cos. T1 cos alpha is equal to T2 cos beta. They cancel each other because there is no horizontal movements. Only vertical movement is there. So T1 cos alpha is equal to T2 cos beta. We take it as T. Take it as 1. So alpha and beta are the angles made by T1 and T2 with the horizontal. Alpha and beta are the angles made by T1 and T2 with the horizontal. Okay. Alpha and beta are the angles made by T1 and T2 with the horizontal. Okay, alpha and beta are the angles made by T1 and T2 with the horizontal. This you know. Okay. Now, from this we get, see, Vertical components are taken as, no horizontal components, only vertical components, minus T1 sin alpha and T2 sin beta. Why minus? Because it is acting downwards. T1 is directed downwards, so it is taken as minus. So the total sum, the resultant is taken as the sum of this. Positive is written first. T2 sin beta minus T1 sin alpha. T2 sin beta minus T1 sin alpha. Applying Newton's second law of motion. Applying Newton's second law of motion, force is equal to mass into acceleration. So total force is T2 sin beta minus T1 sin alpha. Mass is the length into density, mass per unit length into the length. So rho into dx. UTT is the acceleration. Because one time differentiation with respect to t will be velocity, two times differentiation with respect to t will be acceleration. So dou squared u by dou t squared, it is taken as UTT. Here I have written rho into delta x is the mass of the elemental portion AB, and UTT represents acceleration. Now we divide throughout by the tension T. So divide by T. Now from equation 1, I explained already. From equation 1, we write from equation 1, T1 by T is from here. T1 by T is 1 by cos alpha. T2 by T is 1 by cos beta. Okay, and substitute here. T2 by T is 1 by cos beta, so sin beta by cos beta. T1 by T is 1 by sin alpha by cos alpha. Substitute as it is. This is tan beta minus tan alpha, rho by T delta x, dou squared u by dou t squared. Take it as 2. Tan beta and tan alpha, we know from the definitions that they are defined to be the slope. Beta is the angle made at the point B with the horizontal. Alpha is the angle made at the point A with the horizontal by the tensions. So tan beta is applied at the point B of x plus delta x. Tan alpha is applied at the point AX. And when it is slope, the definition is dy by dx. But here it will be dou u by dou x. So same thing. Tan beta is dou u by dou x at the point x plus delta x. Tan alpha is dou u by dou x at the point x. So dou u by dou x of x plus delta x minus dou u by dou x of x is equal to this, because it is slope. One time differentiation with respect to x. Acceleration, two times differentiation with respect to t. Once you arrived at this, divide both sides by delta x. Divide both sides by delta x and apply limit delta x tend to 0. When you divide by delta x, right hand side delta x get cancels. Here it will be dou u by dou x plus delta x minus dou u by dou x at the point x. I explained why. Okay. Now this will be dou squared u by dou x, because already dou u by dou x, again use the formula of differentiation. The formula of differentiability you studied in your PU level. Limit delta x tend to 0, f of x plus delta x minus f of x divided by delta x is equal to f dash of x. So here the first derivative, dou u by dou x at the point x plus delta x minus dou u by dou x at the point x divided by delta x. Limit delta x tend to 0 will be dou squared u by dou x squared equals rho by t dou squared u by dou t squared. Now we write here dou squared u by dou t squared, taking others to the other side. That is, this we take other side, cross multiply, t by rho. And t by rho is taken as c squared. The standard value t by rho is taken as c squared. So dou squared u by dou t squared is equal to t by rho, that is c squared dou squared u by dou x squared. That is dou squared u by dou t squared is equal to c squared into dou squared u by dou x squared. So in the short form, we can write it as, writing it in the short form, we can write it as, what we can write short form. Dou squared u by dou t squared means it is, dou squared u by dou t squared means it is what? UTT. Dou squared u by dou x squared means UXX. So UTT equals c squared UXX. This is called the wave equation in one dimension. This is called the wave equation in one dimension. So various possible solution of one-dimensional wave equation. Next we are studying various possible solution of one-dimensional wave equation. This also might be the question in the exam. So see, now I'll summarize today's class. Today we derived one-dimensional wave equation. In your syllabus, there is 4 derivations in application part. One is derivation of one-dimensional wave equation. Another is solution of one-dimensional wave equation, which I am doing next. Another is derivation of one-dimensional heat equation, solution of one-dimensional heat equation. So each of them is important. It is there in the model question paper. It will come. Anyone will surely be there in the question paper. So next class tomorrow at 11, I am going to discuss various possible solution of one-dimensional wave equation. So I'll end the class today. Okay. So any doubt is there? You can ask me any doubt. If you have any doubt, you can certainly ask me later, or you can tick that and ask when the college starts. Okay. Write the notes. Once again, I'm repeating, write the notes. Writing the notes is the assignment for you. There are two assignments. One is writing notes. Another is assignment 1, which I have given. Okay. And study for the exam. At last, you will not get time. Be serious. So wind up the session. Thank you. We'll meet tomorrow. Tomorrow I'll take one more session at 11 a.m. Thank you. All the best.